అమ్మా ఈ షబానా ఫర్హత్ అంటే ఎవరు? అమ్మాయా?
కావచ్చు మేడం. వేరే అంటే అందరికి సర్క్యులేట్ చేసినాం కదా! స్టూడెంట్ అయ్యుండొచ్చు మేడం మేబీ.
సో వాట్ ఐమ్ ట్రైయింగ్ టు సే ఇస్ ఎవరెవరు మీ ఫ్యాకల్టీ చెప్పేస్తే ఇప్పుడు కోహోర్ట్ పెట్టేస్తా ఇద్దరు ముగ్గురికి.
ఓకే మేడం. పార్టిసిపెంట్స్
రమ్మని చెప్పేసేస్తే వాళ్ళందరికీ కోహోర్ట్ చేస్తే యూ కెన్ మేనేజ్.
ఓకే మేడం. ఓకే మేడం. నేను వాళ్ళకి మెసేజ్ పెడతాను మేడం నేను.
ఎందుకంటే మీటింగ్‌కి ముందు ఒక కనీసం 10 మినిట్స్ ముందనే జాయిన్ అవ్వాలి కదా వీళ్ళంతా.
యెస్ మేడం. వన్స్ అగైన్ ఐ రిమైండ్ ఆల్ ఆఫ్ దెమ్ మేడం. మేడం నేను మెసేజ్ చేశాను మేడం వాళ్ళకి. ఇప్పుడు జాయిన్ అయితారు మేడం. మేడం నిరుపమ మేడం. సౌజన్య మేడం.
Rajita, you were telling anything?
సౌజన్య మేడం
ఎస్ మ్యామ్.
వినిపిస్తుందా మ్యామ్?
వినిపిస్తుంది.
ఓకే ఓకే వెయిట్.
నిరూప మేడం, గుడ్ మార్నింగ్ మేడం.
గుడ్ మార్నింగ్ అమ్మా. అది సౌజన్య కూడా co-host. Saujanya is also co-host. Okay.
ఎస్ మ్యామ్.
Saujanya is also the co-host now. You can also
Yes.
manage the things.
ఓకే మ్యామ్. ఓకే
ఓకే మ్యామ్. ఓకే, థ్యాంక్ యూ.
And this program is live on YouTube.
ఓకే మ్యామ్.
ఆల్రెడీ ఇట్స్ స్టార్టెడ్ మ్యామ్. లైవ్ ఇస్ స్టార్టెడ్.
స్టార్ట్ అయిపోయింది. నేను మీకు లింక్ పెడుతున్నాను, అది అందరికీ షేర్ చేయండి.
ఓకే మ్యామ్.
క్లాస్ అని
చూడు Rajita, I have kept it. Rajita and Saujanya, I kept it. The link it is there in the chats.
ఓకే మ్యామ్, we have seen.
You
Okay,
have
ma'am.
to keep them. I mean, give it to everybody in your groups. Okay. Did the guest
Okay,
come?
ma'am.
Guest వచ్చేసిందా?
గెస్ట్ రాలేదు మేడం. ఇంకా 11 o'clock కి జాయిన్ అవుతారు మ్యామ్.
There is one person who is there. Who is he? Like 1SGRP. 1SGRP 901SAA.
That we don't know, ma'am.
Find out who is he.
He is the research scholar, madam.
Acha. There is some problem అనుకుంటా ఆయన దగ్గర. మీది ఏంటి మీది వాయిస్ రావట్లేదు. I think you have to join with the audio. చూడండి, కంప్యూటర్ ఆడియోనో ల్యాప్టాప్ ఆడియోనో దాంతో జాయిన్ అవ్వాలనుకుంటే చూడండి. I think you didn't click that audio things. Even Shabana Farhat also has got some problem with the audio. ఆయన రీసెర్చ్ స్కాలర్ ఎవరికైనా తెలిసి ఉంటే ఒకసారి చెప్పండి అమ్మా. హిస్ ఆడియో ఇస్ నాట్ వర్కింగ్.
Okay, ma'am. I will inform.
Inform and ask him to rename, and so that I think he wants to speak or enter, but he's not able to reach us.
I'm connected now. Ganesh.
Good morning, sir.
Good morning, madam.
Welcome, sir. Rajita and lecturer in chemistry from Budwell College, sir.
Thank you very much, madam. So still we have some time.
Yes, sir.
Okay, let's wait for the time. Just I was testing, so connected.
Okay, sir. Okay.
Yeah.
Good morning, sir.
Morning, Kirti. How are you?
Fine, sir.
How is going?
Well, sir.
I'm sorry, I forgot to send our SRTP link, this detail to SRTP. I thought 11th I have my one lecture on SRTP. That is the reason I did not forward it.
Okay, okay.
How are you, Ganesh?
Sir,
Ganesh? Ganesh, how are you?
Gayatri also joined it.
Oh, Gayatri is there. So Gayatri can present.
Sir, good morning, sir.
Morning, Gayatri. It is your college, Gayatri?
Yes,
Sir,
sir.
yes, we all,
Gayatri, Niti, Manisha, all belong to TSWRD.
Really?
yes,
Yes,
sir.
So Gayatri have heard maybe hundreds time.
క్లాస్ అయిపోయింది ఒక వెబినార్ ఉంది పడుకున్నాడు అందరు తిన్నారా అన్ని ఎందుకు ఇచ్చినారు నేను మీరే పదకొండు స్టార్ట్ కాలేదు
Hello, good morning, all of you.
Good
Hello.
morning. Good morning, sir.
Good morning, good morning.
Sir, guest
Hello?
sir, Dr.
Okay, okay.
గుడ్ మార్నింగ్ సార్
Good morning, madam. Saujanya, madam, proceed.
Okay, sir, let us start our session. Good morning, one and all. Honorable Chief Guest Dr. Surya Prakash Singh Garu, Principal Scientist, Department of Polymers and Functional Materials at CSIR, Indian Institute of Chemical Technology, Hyderabad. Respected Principal Sir Venkateshwarlu Garu, TSWRDC Budwell, my dear colleagues and faculty members, my dear students, we are delighted and honored to host the seminar on organic solar cells So I am requesting Saujanya ma'am, lecturer in chemistry, TSWRDC Budwell, to welcome all the dignitaries.
Thank you, ma'am. Good morning, one and all. I'm Saujanya. Extends a warm welcome to all of you. On behalf of Department of Chemistry, Telangana Social Welfare Degree College, Budwell, and I want to thank each and every one of you present here for giving your valuable time. Today, we all are here for conducting a one-day webinar with concept of organic solar cells, greener, faster, and cheaper approach. As we all are familiar that solar energy is a renewable source of energy, and our lives are highly reliable on it today and in future also. It's a great pleasure to introduce our distinguished, dynamic, and eminent resource person, Dr. Surya Prakash Singh, who grew up about 30 miles far from where we are right now within a short span of time and contributed enormously for the improvement of the quality of life, research and development at national and international level. Dr. Surya Prakash Singh is a principal scientist at Polymers and Functional Materials Department, CSIR, Indian Institute of Chemical Technology, Hyderabad. He studied chemistry at the University of Allahabad, India, and obtained his PhD degree in 2005. Later, he joined CSR IICT as research associate, working at Nagoya Institute of Technology, Japan, as a postdoctoral fellow between 2006 to 2008. He joined Osaka University in 2008 as an assistant professor in Japan. He also worked as a researcher at Photovoltaic Materials Unit, National Institute for Material Science. Recently, he worked as base fellow at University of California, Santa Barbara with Professor Bazan Research Group. He has been involved in design and of synthesis of functional 5-conjugated molecules for photonic applications and published over 180 research papers at national and international level. He also in three prize winner by Newton Baba Fund, United Kingdom. He also awarded AVRA Young Scientist Award, Bhaskara Advanced Solar Energy Fellowship by Indo-US Science and Technology Forum at California. And he also awarded JSPS DST Special Lecture Tour Program Exploratory Exchange. Young Scientist Award by the Council of Science and Technology Government of Uttar Pradesh. CSR IICT Gaurav Samman conferred by CSR IICT Hyderabad in 2014. Associate Fellow of the Andhra Pradesh Academy of Sciences in 2013. Visiting Scientist, Graduate School of Life Science and Systems Engineering, Kyushu Institute of Technology, Kitayashu, Japan, in February 2013 to March 24, 2013. NASA Young Scientist Platinum Jubilee Award by the National Academy of Sciences India in 2012. So he is also a membership of various professional societies like member of an American Chemical Society and member of an Royal Society of Chemistry London, lifetime member of Chemical Research Society of India, lifetime member Society for Materials Chemistry, lifetime member Luminous Science Society of India. And during under Dr. Surya Prakash Singh, 9 members has been awarded a PhD, and presently 13 members are working as research scholars. So it's a great pleasure to be all of us for being Dr. Surya Prakash Singh as a resource person for this webinar. So I warmly welcome you, sir, and also extend this opportunity to welcome our Dr. A. Bhanuprasad, OSD, TSWREIS, Dr. Rajini Pasupuleti, JETSIO, TSWREIS, M. Venkateshwarlu, Principal of TSWRDC Budwell, all the staff members, research scholars, and my dear students. A warm welcome to all of you. Now I will hand over this to our principal, Sir M. Venkateshwar, to welcome the guest. Thank you, sir.
Okay, Ma, thank you very much. Sir, today we are going to conduct a webinar, organic solar cells, greener, faster and cheaper approach to the topic. So all of you, our children and staff members and other people, and also our ZCO రజనీ పసుపులేటి గారు అండ్ మేడం వచ్చారా? మన సౌజన్య మేడం వచ్చారా?
లేదు సార్,
అట్లా
రాలేదు.
Join అవ్వలేదు.
సో భానుప్రసాద్ సార్ కూడా రాలేదా? వస్తామన్నారు. సో ఓకే 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 ఓకే, నో ప్రాబ్లం. ఆల్రెడీ సౌజన్య మేడం వాళ్ళు చెప్పారు. సార్ డాక్టర్ సూర్యప్రకాష్ సింగ్ పిహెచ్డి కెమికల్ సైన్సెస్ యూనివర్సిటీ ఆఫ్ అలహాబాద్ లో కంప్లీట్ చేశారు. సో వెల్కమ్ సార్, వెల్కమ్ టు అవర్ డిగ్రీ కాలేజ్. స్టూడెంట్స్ అందరూ కూడా మీరు నోట్స్ దగ్గర పెట్టుకోండి, పెన్ దగ్గర పెట్టుకోండి. ఏవైనా మీ డౌట్స్ ఉంటే నోట్ చేసి పెట్టుకోండి. తర్వాత లాస్ట్ కు మీకు వచ్చినటువంటి డౌట్స్ క్లియర్ చేసుకోవాలని స్టూడెంట్స్ అందరికి రిక్వెస్ట్. థ్యాంక్ యూ వెరీ మచ్ సార్. ప్లీజ్ గో అహెడ్ సార్. సూర్యప్రకాష్ సార్.
Thank you very much. I request organizer to make it my sharing screen is disabled. So I request you host to please make it so that I can share the screen. The host disable participant screen. So I request you the host.
Okay sir.
Yeah. Now it's okay.
Sir, allowed, sir. It's allowed.
Yeah, now it's okay. So is my screen is visible now?
Yes sir.
Yes, sir.
Visible, sir.
And I am audible.
Yes, sir. Audible, sir.
Yes, sir. Very, very clear.
Okay, thank you very much, organizer, principal sir, and Dr. Sajanya, my student Ganesh. I am very happy to see many of few of my students. They are the organizer, so I am very happy that to see them again over the screen. And once again, thank you for your introduction, madam. As you can see, I work on solar energy, particular organic solar cell, and my name is Surya Prakash Singh. It is very relevant, Surya Prakash, and I work on solar energy. So maybe it's a coincidence. I'll be talking, basically I'm a chemist, and I request people, participant to mute yourself so that you can listen uninterrupted audio. So it is, my name is very please don't mute me. I request, please do not mute me. So we are chemists. I will tell you how to harvest the sun light to produce the energy. The title is very relevant, greener, faster and cheaper. You know why it is a cheaper? Because sun is available plenty and it is free of cost. And we are fortunate, we are blessed to have in India. If you go other country, the kind of sunlight we have, we don't have like, Europe and many other country. So we are blessed by the nature that we have sun and it is plenty. The requirement is the technology, how we can develop a technology to harvest that sunlight and to produce the energy. Energy is important for as our population is growing. So we want to live our comfort life. So to live the comfort life, we have to have the energy. So there are several forms of energy. I'll be showing the most important sun. There is no any meter. So you don't get the bill for monthly payment for your electricity. Only need to develop the technology. And here is my title of the my outline of the presentation, I'll be showing a little bit about the introduction, particular one technology, that is dye-sensitized solar cell. There I will be talking about the photosensitizer. Photosensitizer means light harvester. Those are the dye molecule. Then another technology is organic photovoltaic solar cell, where electron donor and electron acceptor molecule is synthesized in the laboratory, and it is used as an active layer to harvest the light and produce the electricity. Then the perovskite solar cell, and I will summarize. Perovskite solar cell will be talking about the flexible solar cell, how we can utilize the chemistry to make the solar cell flexible. Flexible means plastic substrate, paper substrate. Those things I will be talking. Before going, these are some of my representative publication and our research area, like OPB. We work on organic photovoltaics, their donor acceptor require, dye-sensitized solar cell, perovskite, and conductive ink. These are some of our representative. Interested participant, colleagues, they can go to my website and download. So before this situation, COVID-19, the energy was on the top, most problem for the next 50 years for the humanity. So still energy is one of the major problem. And this data is the global data, not by me. So energy is the topmost priority for the humanity for next 50 years. Why? We can see our population, how population is increasing. So we should have we have to take care the need, like energy. Then the situation is like this, and this energy currently we are getting from the fossil fuels like coal, gas, petroleum. Those are not, it may deplete one day because it's a natural resources. It may not have all the time. After some time, we may don't have those resources. If you don't have resources, and this is the situation, because this burning the fuel is not the clean energy. So, and result, glacier is melting, and it has many impact on the environment. It is directly affected to our daily life because it destroys the entire ecosystem. Suppose if we don't have the energy resources such as coal, gas, and petroleum, if you don't have petroleum resources, then what is our future? This is our future. What will happen if you don't have the petrol, if you don't have the diesel, if you don't have the electricity? So what is our future? So this is our energy industry ecosystem. There are two kinds energy industry. One is non-renewable and another is renewable. Non-renewable like coal, oil, gas. These are non-renewable and it may deplete after some time. Whereas renewable, it is solar, wind, biofuel, hydro, and others. I'll be talking about the solar energy. Then energy consumption. So far with various sources, how much across the globe, worldwide people are consuming. We can see these are the energy consumption data. Among renewable, though it's a clean and green and low cost energy, but only the consumption worldwide only 2%. Whereas hydro 16%, gas 19%, and coal 40%. So we are burning coal. And if you burn the coal, we are producing the carbon dioxide, which is not good. And the 7% is oil. The nuclear energy is 16%. You know, the nuclear energy is very good. Almost all the developed country, including our country, we have certain plant for nuclear energy. Nuclear energy, we use the radioactive material like uranium and others. But suppose if a natural disaster happens, such as a tsunami, suppose tsunami occur, then what happened? This nuclear disaster, then nuclear disaster also may happen. I am the witness of one nuclear disaster during 2011. If you remember, 2011 in Japan, when big tsunami came, 11th March, and I was there. So the Fukushima nuclear plant, it got blasted. Though I stayed, during my stay 5 years, we never had any problem about the energy because of the nuclear energy. But that day we had the power cut, and there was a huge problem of the radiation because this nuclear power, actually nuclear plant, it got damaged by the tsunami, and tsunami is a natural disaster. So we were forced to move in the shelter, and we were several days in the shelter, and still that area is covered. people cannot go inside because there is radiation and it directly affect. And we know these radioactive material like uranium has the half-life about 35 years. So after 35 years, we have the impact of the those kind of radioactive material. Then, being a civilized country and responsible country, we have certain international norm we have to follow, and this is norm. This protocol was decided in G24 summit for the worldwide, how to reduce the carbon dioxide by 2030. So one roadmap was made. What is this roadmap? One thing, the mileage. Like suppose we are burning 1 liter fuel to run our automobile for 10 kilometers. So we have to enhance the mileage. So let's burn only 1 liter, but mileage have 20 kilometers. I mean, the advancement has happened. Now we have even beyond 20. So one, to enhance the mileage, the energy production efficiency. So efficiency also can be improved. This is the roadmap by the G24. How to enhance? Like suppose if you have 10% power conversion efficiency, we should go 20 or beyond 40. Then that is another way. Lightings, ACs, industrial motor. Lighting, we have the very relevant example. Earlier, we used to have the filament bulb. We all know that filament bulb still maybe somewhere it is there in the village or somewhere. Then it replaced with the CFL. Now we have LED lamp. And we claim, even government gives subsidy, LED lamp. There is less energy consumption. And similarly, ACs, we had window AC, now we have the 3-star, then 5-star, then inverter AC. So these are the help us to in the consumption of the energy, less consumption of energy. Then industrial motor, those are very highly energy efficient industrial motor has come. Another is nuclear, safest way we can install the nuclear, and renewable and biofuel. So renewable is one where one can focus, and that to the sun, because as I say, sun we have the plenty. Then why it's renewable energy resources? Because it do not deplete. Natural resources, it may not deplete. Then the global warming, which has hit the public and political, we know, as I say, glacier is melting. It's destroying our entire ecosystem. Effective method to reduce the carbon dioxide emission, we should have that. Then guarantee energy security. And the government also, they have passed the legislation, and then government have the Jawaharlal Nehru Solar Energy Mission Program. And there we are working there, and we have several program funded by the government. Then the key renewable energy resources are, these are the solar power. Among solar power, photovoltaic and solar thermal. Then wind power. Wind power means onshore and offshore. Biofuel in agriculture crop, that is first generation, second generation, and third generation. And first generation contain the agriculture crop, the second generation cellulosic feedstock, and third generation is algae. And hydropower. I will be talking about the photovoltaics, that is our area. And this is, as I said, that the title of our talk, it is a greener, cheaper, and faster. So it's a green and very fast and low cost. How? So this, before I explain this, actually it will explain itself. You can see this device also called sandwich solar cell. It is a Dyson-sized solar cell. It also known as a sandwich solar cell. If I say sandwich, everyone knows sandwich. Most of the people that take in the breakfast. Sandwich, what is sandwich? One bread down, one bread up, in between masala. That is the sandwich. So it's very cheap. You know, it's very cheap, easy to fabricate, easy to make the solar cell device, and it's very low cost. So how to develop? You can see here, the one TCO glass is this side, one counter electrode this side, and in between masala. If I say masala, it means it's a dye molecule and other component, that is light harvester and redox couple. If you see this diagram, how the sunlight is coming onto this, the right hand side of the diagram cartoon, when light fall on any molecule, its electron get excited. It goes from ground state to excited state. And then there it retains some time, and again it come back to the ground state. And we have studied this in our junior high school also. So how we light our lamp, light while crossing the road, we can see the signage, signboard. like speed limit 40 kilometer, danger area. So once our light fall onto it, it's a fluorescent material. It get, its electron get excited, and we used to read those signboard. But once we pass through, then again it comes to the ground state. We cannot see those signage. So similarly, you see once light fall onto the molecule, its electron get excited, it goes to ground state to excited state. And again, it come to ground state. But if come to ground state, then we cannot generate the energy. There we use the redox couple. So redox couple we use, and you can see their electron, again, it is regenerating. So if you have this technology, and then we have the easy way to harvest energy and produce the electricity. The advantage is it contains the low manufacturing cost, no vacuum. And since it is a chemist, the light harvester are the organic molecule. So we can make the colorful device. We can make the colorful, and which gives the very aesthetic look. I'll be showing later. These are the advantage of dye-sensitized solar cell: transparent, colorful, flexible, easy process, and so on. And it can be improved. These are the few demonstration by the Toyota company in Japan, and I am privileged to work 1 year in this company. It called the Toyota. It's in Cosmos. You can see this colorful tree. It is and see the flexible device. You can see this window and transparent. That angle of incidence. The window means we use window as a to protect our privacy, to protect the dust, wind, and so on. But window is unutilized area of our place, of our building. But if you have this device, from window also we can harvest the energy, and at least one light we can we can generate some energy to light at least our one room. The beauty of this technology, it work under diffuse light. Now all the solar cell available in the market, it is based on the silicon solar cell, and we don't have silicon in abundance in our country. So we have to get it imported by other country. And the current scenario, you can see that this all depends on our political relation to import anything from the different country. And it require high process. We have to use very, very 99.99% purity of the silicon. And then it is not energy efficient. But this dye-sensitized solar cell, it work under diffused light, whereas solar cell, silicon solar cell, it has to face towards sun. Like sun, we know that it moves from here, like this. Then people use the solar tracker. Then our panel also move according to sun. Then it's not very cheap. Common man cannot install. Whereas this technology, it work under diffuse light. Diffuse light means we have this light. There also it work. We don't have to face towards the sun. So this is the beauty of this technology. Anyone can guess what is this? This is a photosynthesis. It is occur, naturally, photosynthesis. That's what plant, they make their food and they survive. Then what is there? How they get the carbon dioxide and water, and they produce the sugar, the carbohydrate. Then that is their food. But what is the important component it require here in the photosynthesis? You can see sunlight and chlorophyll. These two factors is required to make plant their food. So it's called photosynthesis. And we know chlorophyll is a dye molecule. It's a color compound, and light we get it. Based on this, researcher, they inspired to use this photosynthesis into the dye-sensitized solar cell. The dye-sensitized solar cell is based on photosynthesis. The chlorophyll is a dye molecule, but we cannot get chlorophyll from the plant. We cannot cut the plant and get it, and moreover, those are not very stable. So we have to develop those kind of are better than the better dye in the laboratory. So we synthesize the dye molecule that I will be showing here. If one want to do research in the dye-sensitized solar cell, then what are the component? These are the 4 major components to work in this technology. One is the TiO2, another is dye, electrolyte, and device. So dye, I'll be presenting about the dye, how to develop a good dye. We have so many development, lot of advancement. but I will not go much technical because I don't know how many of you chemist. So the criteria to design an efficient dye, how to design. So this is a solar cell. Solar cell is solar spectrum. Sorry, this is a solar spectrum. The red color, you can see the sun spectrum. It looks like this. So if we have a dye which can give the similar kind of a spectrum absorption, then we can harvest all the photon present in the sun. But it's not so easy. You can see the blue line, the desired one. If we have any sensitizer which can harvest like this blue light, then we have chance to harvest all the photon. But effort is being made globally. All entire the researcher who is working in this area to develop a good sensitizer, and they could able to achieve up to this one green one. So the researcher are able to harvest only this much light from the solar spectrum, but our desire is more. Then what kind of a prominent light harvester researcher they have used? You can see down one is the ruthenium complex. So this ruthenium complex is also known as N719 dye or red dye. So this is the 2 bipyridine ring connected with the coordinated with the ruthenium and 2 NCS thiocyanate group. This is the one dye which people they have used it here. This is the main. So this is the metal complex, as I say, red dye. So you can see 2 bipyridine is connected with the coordinated with ruthenium metal with 2 thiocyanate group NCS. But NCS is not very stable. It's very labile. Who knows the chemistry of thiocyanate, they understand. Our solar cell has to face in towards sun, and in our country we get temperature 47, 48. So under those conditions, this NCS group is very labile. It may cleave during the, then A, what is that A? It is for the anchoring group. Our anchoring group should bind with the semiconductor, that is TiO2, and then extend the pi conjugation. We know if we extend the pi conjugation, we get the better absorption. So this is one model to how to design a metal complex. We tried here to develop few sensitizer. You can say red, blue, and pink. The one is the biquinoline and pyridine and quinoline. You can see these 3 complexes. And these are the absorption. The bipyridine is giving bipyridine complex giving 530 nanometer. Pyridine quinoline is giving 580 nanometer, and biquinoline is 625 nanometer. If you have heard about the concept, with the concept, if you have more absorption, we'll get better light. You see, it means, we'll get better energy. So this 625 nanometer will give the more efficiency. But when we constructed the device, you can see the right-hand side of the slide, the IPC with the pink one, it is going very down. There is no current, no efficiency, though absorption is very good, 625 nanometer. Then where is my concept? It means what concept I discuss, it may not valid. No, not only this, we should have it's a homo-lumo also matter a lot, like ground state and excited state. It's a matter a lot. And I think, here, this homo-lumo, it's a matter a lot. So our lumos should always lie above the conduction band of the TiO2. Otherwise, electron injection is not possible and we may not get the energy. As I said, we have developed many metal complex, but I request host not to mute me. Otherwise, you may not able to listen me. Okay, I have unmuted myself. So we have developed many sensitizers, many metal complex, but this is only one example. This is a black dye. It is known and available commercially. And the HIS2 is synthesized by our laboratory. And if you see the data and table, you see the HIS2 is giving 11.1% efficiency, whereas black dye is 10.5%. So our dye is much, much better than the reported one, commercial one. What happened? Yeah. So based on this concept, we have developed a series of metal complex. We have many more. Few of them I'm presenting here. Now the question comes, as I mentioned, this is a very cheap technology, but ruthenium is not the cheap metal. It's ruthenium metal is not very cheap. So how I can claim it's a cheap? Then we move, considering this cost, we move towards the metal-free sensitizer, metal-free dye. You see here, then we have developed a series of metal-free dye, a simple organic molecule with a good power conversion efficiency. You can see this porphyrin, triphenylamine, porphyrin, triphenylamine, and this indolin, fluorine, perylene, and diketopyrrolopyrrole. This kind of sensitizer develop in our lab. The concept what we follow in the middle, if you see, it is a push-pull kind of system. We have one electron donor, then electron rich pi system, then electron poor pi system, then cyanoacrylic acid, that CN CO2H. That H will bind with that hydrogen atom will bind with the TiO2. So based on this push-pull system, we have developed this, and in our laboratory now we are achieving over 12% efficiency with with metal-free dye. As I say, our device efficiency is only up to 12%. So how we can achieve further, because 12% is not enough. And again, if you look this solar spectrum, with one single dye, we are able to harvest only limited. So we thought, can we have two dye in the system, like dye 1 and dye 2? And if you see down here, tandem cell, dye 1 will harvest up to 300 nanometer to 700, and another dye will harvest 700 nanometer to 1300. So if two dye, if you mix together, it will complement each other and we may get high efficiency. So this is called co-sensitization technique, or mixed dye sensitized solar cell, or cocktail dye sensitized solar cell, because two dye we are mixing together. So after this concept, we thought, let's try it. Here we have tried two dye we have mixed together, and if you look into the table, the one dye is giving about 4.8%. When we are mixing, we are getting 8.1%. Please remember, this is not for high efficiency. You can ask that why efficiency is not very high. This is only proof our concept, whether this concept is working or not. And you can see one dye is giving like one number, then mixing two dye going to double. So the concept is valid. Again, you can see the at the down slide, you can see JD1 is giving 4.76%, and then JD1 with SPS1 giving 8.3%. It means our concept is valid. Based on this, we have developed a series of, we have, I think, more than 24 paper on co-sensitization system. Now coming to the purity. Purity is another important factor which matter a lot for dye sensitized solar cell. Here we have compared black dye with commercially available. You can see purple color, and blue one is our. The same dye developed, one purchased from the commercial source, one developed in our lab. And you can see how current we are getting more. So purity is important. Now coming to the transparent solar cell. Many of you have been to IICT. You can see IICT building looks like this. Now we have worked on the transparent solar cell. As I say, transparent, we can see from this side to that side. And it looks gives a very aesthetic look, very beautiful look. And as I say, window is our unutilized area, and it can be utilized by harvesting the light. So you can see we have developed this dye, and we have used for the transparent solar cell, and it is printed on the glass substrate. So it is good. Not only this green, since we are a chemist, we can tune the color from, and down you can see these all color developed in our lab. And some of the participant and faculty of this seminar, they work in my lab, and I think they have synthesized this all. You can see our nanomaterial building. We can see from this transparent solar cell from this side to that side, and here is the gel in the middle. And the concept, we have used our catalytic system. I do not want to go much technical chemistry, and just I will mention we have used the CH activation, like coupling process. If you want to do Suzuki coupling, we have to use the boronic acid and catalyst to use that, and we have to use 2 coupling partner with which has the feasibility to couple each other to make the CC bond. Here we have used just CH activation to get this compound, and the efficiency is also 9%. As I say, chemist can tune the color. This is one example. We have tuned from green to blue. Just see the molecular structure. Just simple. Having these 2 cyano group was changed and the color is changed. So just change the chromophore, because chromophore is responsible for the color. In my talk here for the dye-sensitized solar cell, I will take you to another technology that is called OPB, organic photovoltaic solar cell. What is that OPB? In OPB, electron donor and electron acceptor material is used, and the research direction, it contains 4 component: electron donor, electron acceptor, hole transporter device. The electron donor is generally polymer or a small molecule. Electron acceptor is fullerene or non-fullerene. The advantage of this technology, you can see, we can print this technology. We can make the ink, fill in the cartridge, and use your substrate and print the solar cell. And then you can make the roll to roll. You can roll your solar cell. But disadvantage, solubility of fullerene. Fullerene is not soluble. We know fullerene. I'll come to the fullerene. What is the fullerene? It's a buckyball. We have studied, I think, in 10th standard, 9th standard. So what is the buckyball? And the polymer is not good, because any polymer chemist who studied the chemistry of polymer, they know that we have to have the monomer and then we have to polymerize. So if we polymerize, suppose today we are polymerize of the monomer, we get suppose 12,000 molecular weight. Tomorrow we may get less or more. So there is no consistency in the molecular weight. So molecular weight vary batch to batch. And if molecular weight vary, then power conversion efficiency and performance also vary. So we have moved towards the non-fullerene acceptor. Then coming to the a kind of quiz question, what is the carbon allotropes? We have studied carbon allotropes. It is a diamond, graphite, fullerene. And the fullerene buckyball, we know it also known as a Buckminster fullerene, which was discovered in 1985. And chemistry Nobel Prize for this Buckminster fullerene, for Croto, it was given, and Smelly, it was given to in 1996. Then how it looks, the fullerene looks like this. It is a 5-membered ring surrounded by 6-membered ring. Then I asked only question when I teach the PhD student in our institute, then how many pentagons and how many hexagon, how many 5-membered ring, how many 6-membered ring? So 12 pentagons, 5-membered ring, and 20 hexagon. And then we get, this is the fullerene. When you dissolve in solvent, it looks like this. It looks like a pink color. Fullerene is like that. Then what about the availability? And also I'd like to mention this carbon allotropes is a good material, and the graphene also got Nobel Prize in 2010 and the University of Manchester. And I was fortunate to visit University of Manchester during 2014, and I have met those professors. And you can see here, but availability of diamond and gold, availability of fullerene, carbon nanotube, how much graphene, how much availability in the country. Gold is available a lot. We know that about 34,000 ton actually, whatever government data, Ministry of Commerce data say, 34,000 ton we have gold in our country. And similarly, maybe the diamond. I mentioned the diamond because, we are talking about the carbon allotropes. How about the fullerene? I work in fullerene. If I want to buy 10 gram, we have to wait for 1 month or 2 months to get from the abroad. Similarly, getting 1 gram, 2 gram carbon nanotube, graphene, it's not so easy. We have to wait for 1 month or 2 months. So can anyone work to get this? If anyone work, availability is very, very, we have the gold and this diamond, we have plenty. Whereas this carbon material, we have very limited availability. If anyone want to work on this, they can become millionaire. And please, if you become this work, inform me, because I am giving you the idea. So coming to the now the another electron donor material. This is the before that electron only polymer was used and not the small molecule. This is the one where for the first time this small molecule was developed by Professor Bajan and Heeger. And Heeger, he got Nobel Prize during 2000 from University of California. And again, I am fortunate during 2015, I went and I worked about 6 months with Professor Heeger and Bajan. And I learned what are the new technique and how we are utilizing those technique in our lab. And that's what our students, they are getting highly benefit. So this kind of like a C2 symmetry molecule, you can see like core and wing. Core is the silicon derivatives, red one, and wing you can see that others. And this is the one synthesis, 6.7% efficiency. And during 2011, the work was also published in Nature. I will not go through the chemistry part, the coupling. Mostly the Stille coupling was used to synthesize this. During my stay with Professor Bajan and Heeger, this I was synthesized. I synthesized this material, and we have published in. And here the power conversion efficiency was 9.1% using the small molecule. Please remember, we have removed the polymer. Now we are using a small molecule and getting the better. A small molecule, we can tune its property further, whereas polymer we cannot tune. Then if you look into this here, the material, the germanium is used, and this germanium core, it's called a dithionogermol. It is really expensive and very tedious to synthesize. And we really tried here in IICT, almost more than 5-6 months we tried. And then we failed actually, we could not synthesize. But during my stay at University of California, I could able to synthesize this. The reason still we don't know, but those are very tedious to synthesize and tedious to, and lengthy process and expensive. When I come back to India, and then we started this diketoperidopyrrole. It's a very cheap material. Diketoperidopyrrole is very cheap material, and it is used in many applications. One of a student, he was dedicated only for this, and now he's in abroad. So DPP is a highly efficient and stable material, and it's very cheap. You can prepare in a ton scale. It was discovered in 1974, and then it was commercialized in 86. It is used as a pigment. Whatever pigment we see, like paint, plastic, fiber, ink, those all pigment, even including our cloth, like fabric. Excuse me. Even including our cloth, this kind of pigment is used. The synthesis is very simple. See, take the thiophenol carbonitrile, you get the DPP core. And if you see at the last dibromo DPP, diketoperidopyrrole with dibromo, if you have dibromo, chemists understand, if you have the dibromo, you can couple any kind of chromophore there. You can have any kind of moiety you can attach there by coupling reaction. So this was, and it is very cheap and can be produced at large scale. Then this work was done by Dr. Narayan Swamy. Now he's in Paris, France. So you can see this small molecule following the same concept with core and wing. Though efficiency is not good, but it's a very, very stable compound, and it's very cheap. This is the synthetic protocol. So as I said, I will not go detail how to synthesize this molecule. Now coming to the another concept, donor acceptor. As I say, this technology requires donor acceptor. In the I request organizer, if my time is over, please notify me, so I will stop my presentation immediately. So this is the donor acceptor. You can see donor acceptor we have to mix together. Can we develop a molecule which can only work the single? No need to mix donor acceptor. Donor acceptor in the same molecule. Like you see this chart will show you how two people working together, and 1. So it's energy efficient. One person can work for 2 people job. Again, the work was done by Dr. Narayan Swamy. You can see we have developed this is donor acceptor in the same unit with 2.1% efficiency. I'd like to mention here, this was the highest efficiency during 2016. Now we have better efficiency, and the work was also published in a very high impact journal. Then these are the fullerene. As I say, fullerene has the solubility issue, and we have synthesized a series of new fullerene derivatives. And you can see here we have many, and we have some paper and patent also. These are highly soluble. This is the commercially available material called PCBM, and it requires the 5-step process to synthesize. But the cyclopropane ring at fullerene connected to that organic moiety is not the stable. Cyclopropane ring you can see here. You can see here the cyclopropane ring. It's not very stable. So we have developed the single step process and working better than the fullerene. I mean PCBM. And this also got patented. Soon it will be the commercialized. Based on this, Dr. Nagarjuna, he developed his Nagarjuna. He's my first student who have synthesized this all material, and now he has he's also in abroad. Some of them are published, and few we are planning to publish. Again, coming to the fullerene, as I say, it is not good. It is the having less absorption window and low solubility. So we thought, and it's expensive. As I say, solubility is very low. So we thought, can we move towards non-fullerene acceptor? So when we look into the non-fullerene acceptor, what are the concept? As I say, the fullerene is a 5-membered ring surrounded by 6-membered ring. When we look into the literature, we found that you can see the blue color moiety. It is a fluorine, and fluorine is 5-membered ring surrounded by 6-membered ring. And one of again my student, Dr. Suman from Rajasthan, she worked these all project, and she has developed many, and we are able to achieve up to 11% efficiency. The beauty of non-fullerene acceptor over the fullerene, its absorption is very good, easily available. We can synthesize with organic material, and it's a very cheap, and purification is very easy. So here is the concept, how it was developed by Dr. Suman. You can see here from 7% to, and we have now replaced the fullerene, no fullerene required. So I will end my talk here for the OPB. I will move to perovskite solar cell. Perovskite is the now one new technology where people are working and achieving very high efficiency, and our group is also working in a large scale. But concept is different. Can we, with perovskite, can we coat our wall, our house wall, so that house wall also is unutilized? So we can see where one concept we have formulated, but we don't have great success here. So we are planning like a solar paint. So this perovskite we are using, and this HTM, whole transport material, is very expensive. So right now we are working on how to replace the whole transport material with this. So these are the whole transport material. We are able to get about now 18% efficiency with our new whole transport material. The perovskite, it contains the lead perovskite, known as lead perovskite. Lead is toxic, which is not good. So we have to replace the lead with other metal. So here is the one we have replaced with lead free, the cobalt one. You can see the cobalt, we are able to grow the crystal also with 3 mm to 5 mm. This was done by Dr. Ramoth Babu, who work in our lab as a postdoc. And also, can we reduce the lead content by doping? The below slide, you can see how in cesium lead chloride, we have doped the iron. Why iron? Because iron is available plenty in our country. So we have doped the iron, and you see how the color change from blue to pink. And it may show the good property for the OLED, light emitting diode. What is light emitting diode? You know, in a smartphone, we get different kind of multicolor. In the TV, in the even desktop, how we get. So these are the OLED material. So one can utilize this as a OLED material, and it's so dual emission. Now I'll come to the flexible solar cell. What is flexible solar cell? So this work was done by our dissertation student, one team. So you can see we have developed a conductive ink. Like if we are making the panel on the plastic substrate or the glass substrate or the paper substrate, if we connect the wire to, to travel the electron, then wire is not, not good. We cannot fold it because it's a wire. So can we develop the material where wire is not required? I mean, for the flexible substrate, you can see here the CSIR ICT was written on the paper and there is no wire. And when we have given the current, you can see it is lighting, and here Science and Technology Minister here. I will show one movie how this material it work. So this is the printer. So we are doing manually on the paper. It is just I think very small video. I request to please see. It's a 1 minute 20-second video. You see, we are checking the conductivity. It is printed on the paper. The conductivity was checked with those are the material was printed on the paper. Now, this conductive ink, it based on the silver, and you see we are giving now current. You see the lighting, so there is no wire. It is very good. Now you can see in the market, now the new TV is coming, foldable mobile phone is coming. So there you don't have all the circuit. It is now printed by this. There is not a single Indian company who produced this conductive ink. And you can see here, the device is printed on the paper. So now I'll take you to the yeah. So this is, here is the another, you can see with the industry, how the piano and other was used by there is no wire. You can see it is on the flexible substrate and it is being used.
Sir, the slide is not moving, sir.
Are you able to see?
Slide is not moving, sir.
Okay. I'll go to again. Now it's okay. Now it's moving.
Sir, yes. Okay, sir.
Okay, so this is the development for our flexible devices, and you can see our Science and Technology Minister also visited to our lab, and we have a lot of encouragement to work on this. And then I will skip this because you see here our dye-sensitized solar cell, how we had one car race in Japan, and this dye-sensitized solar cell, the car was made by this our dye, that ruthenium dye, and you see here, and it was won by the Mitsubishi. And you see here, we participated there. You may not see my photo because I was the cameraman. I was taking the picture. So you can see this car race was done here. This is for the flexible devices. And then this is for the color material, the flexible devices. This dye, actually, it cannot be used only for the solar cell. It has several other applications also, beyond the solar cell. And I will show a few slides, then I will close. This is for security printing. What is security and forensic printing? So this is very much important for the country, for the government. You can see our dye. This is under daylight on this paper. It is not visible anything. Whereas when we irradiated 365 nanometer of the light, you can see CSIR IICT. It is visible. We have good expertise to develop such a dye molecule. And we also formulated the ink. You can see here, this 2 refill was filled by this ink and it is written there. So the dye is not only for the energy harvesting, it can be used also for the security printing. So here is one example. And then it can use also for the ink to refill. You see here, and it's a very stable ink. We have developed the black ink. This also done by the one digitization student. The black ink was developed. The beauty, it is stable in the water. Not only even at 70 degrees centigrade for 1 hour, and that's enough because we have not gone beyond 1 hour. our dye is also formulated the ink to refill it in the ballpoint pen. It's very stable. Blue ink also made and formulated the ink. Similarly for the paint, we have replaced the lead and cadmium free paint. Lead cadmium is not good, though we get the very fancy paint and we coat our house. That's not good. So we have the lead and cadmium free paint, the pigment for the paint industry. This is the work where I'll present here. This work done by Dr. Gayatri. So I call Gayatri. So she is also the faculty member of this event. She is really one of very bright student of mine. She has worked on the body P molecule. And you can see this body P also is known as a little sister of the porphyrin. What is porphyrin? Porphyrin is available in our blood. That's our color is red because of the the porphyrin. We have that heme. That's the structure is the porphyrin, and she has worked on this molecule. You see here, she has developed a very good component, and some of the material actually today only morning we have signed the agreement. This all molecule is going to for a Japanese company. They will commercialize. I think Gayatri, your work is recognized and Japanese company is now buying. And today only we have given the document to the CSIR headquarters. Maybe within a week, this all molecule will get commercialized by the Japanese company. This all you can see was developed as for the gel material, and you can see how cooling and heating, the nature of the material you see here. This is the cement AFM images, the single rod. Color also is changed. Work was done by Dr. Hanumantrao. Then coming to the photochromic material. What is the photo? We also utilize this for some kind of fancy product. Then photochromic material, which is photochromic name itself is governed by the photo. Which is the the reaction. You can see here, this one is the one vial here. It is transparent. When UV light is irradiating, we are getting the red color. Then how it can be used for the fancy product? You can say the nail polish, under dark, it has the different color, but under light, it has the different color. Same thing for the paint. You can see the thread. You can see this sandal, and so on. So this photochromic material has several advantages for the various fancy product in the textile, t-shirt and printing. We have one in-house project funded by ICT. We are working on it. You can see here how we have this our project. We want to make the ink of this photochromic material, fill in the cartridge and print it. So if you print, our t-shirt will be like this. If you go in the dark light, there will be no color. No, and if you come into the light, we'll have the different color. So like, it will govern. We have a good team. I will skip. Our recent project, we are working, developing the sustainable dye for the fabric, for the textile industry. Why? Because the textile industry is now suffering with the paint, because the paint they are using, then they are just throwing in the nalas and those going to our rivers, which is polluting. And if you have heard that we buy the cloth and we wear and we don't see the consequences, what is happening behind it. A cloth actually, when it dip into the color material, then those color, what happen? Either it goes to our groundwater, which is not good. It is contaminating our groundwater, and maybe our next generation, definitely they will suffer with the water problem. But can we develop some dye for textile industry, which may generate the less effluent? And if you see that in the rivers, the fish are dying. Fish are dying means, it's not only one fish is dying. It's a destroying entire ecosystem if one fish is dying. So this funded this work we are doing for the industry. And these are some facility we have in our lab. We have absorption, we have electrochemical workstation, we have the CV to measure the homolumo, and here we have the screen printer. You can see we have the solar simulator. The artificial sun. We can generate it and we can measure it. And then these are some commercial module. This is the DSSC module by the Toyota company. It is in Nagoya at Korea City. We have been there. These all the Israel module. These are the organic solar, the DSSC module by the Professor Gretgel. Toyota Dream House. If you visit to Nagoya in Japan, you can see I was there about 1.5 years. This is also by the Shinseki Toyota company. This also same fancy product, transparent DSSC, flexible and transparent. You can see the leaf from this side to that side, and it's transparent. It is printed on the plastic substrate. G24. Even now you can buy any product from G24. This is the company. You can buy the such kind of mobile charger, other thing. The flexible, I mean the roll to roll. This is OPB. You see the device solar cell is getting printed. So it's a hybrid car. This mobile charger and backpack. I will end my talk, and I'd like to acknowledge my all student. They are really very hard work, and in general, the scientists, they don't work any work, only student they work. And I'm fortunate to have very good team in the IICT, and all the work I have presented, it was really hard work of my all students who work very hard to produce this. Also, I acknowledge my present director and former director, my HODs, and my collaborators, and funding agency also like IICT, DST, India-US Forum, Indo-European Forum. These are the main funding, and some industry, if they don't fund, we cannot do any research. And I thank you, all of you. And now I'll be happy if you have the question. I would like to answer it. I'll try to answer it. Thank you very much, organizer, to invite me and giving the talk. Thank you so much.
Thank you, sir, for sharing such a valuable knowledge for all of these students.
Thank you, madam.
It's very thankful to listen such a webinar, sir, on solar energy and allotropes of carbon and dyes. So I request students and the participants to ask any questions regarding.
You unmute, the participant can unmute and can ask question. If not, they can share in the chat box. So I am able to see. If you are unable to, your mic is or audio is not working, you can just chat. I can answer both ways.
Hello, sir. Hello, sir.
Yeah.
Sir, good afternoon, sir. I'm Soumya.
Yeah, Soumya, good afternoon.
Talk was very impressive, sir. It was very good. So I have a doubt in perovskite cells, sir.
Okay,
so
you tell me. I'll try to clear your doubt. Yeah, Soumya ji, please. Soumya ji, please. I'm unable to hear you. Can you please unmute yourself and then?
Yes, sir. I have unmuted. Is it audible now?
Yeah, I'm audible.
Sir, you have told it that you're coating it on walls, right? Perovskite
Not
material.
coating. That is our future plan. Like I said, paint. That is our plan.
Yeah, but perovskites are water unstable, right? When water falls on them, the perovskite cell breaks,
But
right?
paint
Sir?
you are coating. That's the technology that you have to use, the physics, chemistry, and engineering. So if you have the paint, and you have to, it will be the protected. It will be sealed like in the cap. Once in the cap, and once it process, then it cannot be further, damage.
Okay, so you are coating it on paint, like on the wall first perovskite, and then over it paint
I would
will
like to say we are not coating right now. We are making the test cell device on the glass substrate. That is our plan.
Okay, sir. Yeah. Okay, sir. Thank you, sir.
Yeah, welcome. Any more question? I'll be happy to answer. Participant, please. Organizer can ask the participant for the questions. If anyone is not audible, they can share their question in the chat box. I'm able to read that chat box and I can answer. The organizer, I request organizer, you can announce the participant. They can ask if they have any doubt or they have any questions.
Okay, sir. Okay, sir. All the participants, if anyone have questions, please message in chat box. I will convey your questions to the sir.
If they are audible, they can ask also.
Yes, sir. If they are audible, they can ask.
Yeah.
No problem, sir. Someone messaged, sir. Sir, how to apply for the projects in IICT?
Let you have my email address. You can get from ICT website. Write me email. I will definitely guide. For PG student, we have our academic affair unit. You may directly contact there. We have the contact au@iict.res.in, or you can directly write me from my email address. I can share my email address, and then I can guide you. And we are very happy to actually help being a national laboratory. We are very happy to help all the PG. And right now, I think we are mentoring 5-6 students online. So ICT always welcome to the PG students. And you can write me directly. I'll definitely help you. I'll connect to the concerned people.
Okay, thank you, sir. Thank you for your cooperation. Someone messaged, sir, how many?
Yeah, how heterocyclic this Kirti ask how many heterocycle system can we develop for metal-free dye? What is the scope of bioligand? Yeah, bioligand means there is no any such a kind of the criteria how many heteroatom you require. Even without heteroatom also it works. Only thing, the main criteria is it's a homolumo. It's a ground state and excited state. It should be always below the conduction band of the TiO2. Otherwise, electron injection is not possible. Yeah, the Sri Priya, here is my email address. I'm just typing. You can write spsing @iict.res.in. Here I'm typing spsing @iict.res.in. And these days, getting email address is not very tough job. You can go to ICT, type my name, you will get the email address. Anyway, I have sent Cypria my email address. Yeah, welcome. Any text message or any question, please? It seems that there no question.
No questions. Yes, sir. It seems to no question.
Then if you have organizer have anything, then I will stay. Otherwise, I will leave the meeting.
Yes, sir. Yes, sir. I am Rajita, lecturer in chemistry, TSWRDC Budwell. First of all, I would like to thank you, sir, for spending your precious time for us. And also I want to congratulate you, sir, to commercialize your products with the Japanese company.
Thank you. Thank you. Actually, those all credit goes to my student Gayatri. I think she's faculty over there.
Oh, okay, sir. Gayatri ma'am, actually faculty of TSWRDCW. I am also congratulating Gayatri ma'am.
I always encourage her to go to IIT, go to abroad.
Thank you, sir. But without your guidance, it wouldn't be possible, sir. So I should thank you for that. I'm really lucky to have such a wonderful guide who supported my ideas. Yes, all the way. I'm really happy, sir. I'm really thankful to you.
Thank you, Gayatri. Welcome always.
Thank you, sir.
So, Ranjita madam, anything else or shall I leave the meeting?
Yes, sir. Yes, sir. Wait, sir. We want to vote of thank you. Okay, sir. Several in our group have expressed appreciation for the information you presented on organic solar cells, and your talk was particularly appropriate at this time. And because when we are considering new initiatives to overcome global warming and the lack of non-renewable energies, And we particularly liked hearing about solar dye sensitized solar cells and application of photosynthesis to development of dye sensitized solar cells, co-sensitization and organic photovoltaic cells, and so many things we learned about by your seminar, sir. We are feeling great to meet you, sir. Thank you, sir.
All are welcome once situation is normal.
Okay, sir. Thank you, sir. And I'm requesting Vice Principal Madam B. Jyoti ma'am to vote of thank all the participants. Okay, ma'am, maybe not participated, not attended. So, good afternoon, everyone. Honorable Chief Guest Dr. Surya Prakash Singh sir, respected principal, and my dear colleagues and faculty members, and my dear beloved students. It is my privilege to vote of thank all on the behalf of TSWRDC Goodwill. First of all, I am thanking you, Dr. Surya Prakash Singh sir, for spending his precious time for us, and I am thanking. I want to thank Principal sir who guided and encouraged continuously, and student familiar guidance. And also, I want to thank all the faculty members to make our event success. And dear students, I also want to thank all of you. Thank you, sir.
Thank you, madam. Thank you. Bye bye.
Okay, bye.
Thank you, sir.